Hello viewers, we shall continue our discussions on probability theory. In my last lecture, you remember we have defined the random experiment, the sample space, event and equally likely elementary events. Using these concepts, we have defined the probability, the classical approach of probability. This is also known as the m by n definition of probability. In the second part of the lecture, we shall discuss frequency approach to probability and its limitations, the additive and multiplicative laws of probability and their applications. Finally, we shall discuss independence of events. The additive and multiplicative laws of probability and concept of independence of events help us to compute simple and complex problems of probability. Let us first discuss the relative frequency approach to probability. In early 19th century, the British statisticians got interested in the foundations of calculating the risk of losses in life insurance and commercial insurance. And this approach used the statistical data collected on births and deaths. The relative frequency approach is based on the relative frequency of occurrence. It also depends on the observed relative frequency of an event in a very large number of trials, or the proportion of times that an event occurs in the long run when conditions are stable. For example, an insurance company knows from past actuarial data that of all males 40 years old, about 60 out of every 100,000 will die within a year. Then the probability of death for that age group is 60 divided by 100,000, or it is equals to 0.0006. In other words, this provides an estimate of the probability of an event A, where event A denotes that a male 40 years old will die within a year. This approach relaxes the two major assumptions of classical approach. We remember that the first assumption in classical approach was that your small n, the number of possible outcomes, is finite, and the second was all elementary events are equally likely. So, in this approach we can get rid of these two assumptions. Now, I am going to discuss some important results on probability, and these results are true for all the three types of approaches to probability, whether it is the classical approach or the frequency approach or the axiomatic approach. The first rule is called the addition rule, and it is that if A and B are two events, then probability of A union B is equals to probability of A plus probability of B minus probability of A intersection B, or this can be written as probability of A or B equals to P of A plus P of B minus P of A B. Now, let us see how we can apply this rule. Now, consider an example of a playing cards. We know that there are 52 cards in a deck of playing cards, and we are interested to find the probability that a card drawn at random from a deck is either black or a face card. Now, here we define the event A as of getting the black card and the event B that the card is a face card. Then by using the m by n definition of the probability, this P of A is equals to 26 upon 52, because the number of possible outcomes of the experiment, that is small n, here is equals to 52, and the number of black cards in this deck are 26. Therefore, when we are selecting one card at random out of 52 cards, then this probability is 26 upon 52. Similarly, the probability of B will be 12 upon 52, as there are 12 face cards in the 52 playing cards. That is, the 3 face cards of each of the type of card, that is club, spade, diamond or heart. So, this probability is 12 upon 52. Now, we are interested in finding out the probability that a card drawn is either a black card or a face card. It means, we are interested to find out the probability of A union B or probability of A or B, and by the rule 1, this is equals to 26 upon 52 plus 12 upon 52 minus 6 upon 52, that is equals to probability of A plus probability of B minus probability of A intersection B. Here probability of A intersection B is 6 upon 52, as the number of common elementary events between set A and B are 6. Now, let us consider another example. Suppose the employees of a certain company have elected 5 of their number to represent them on the Employee Management Productivity Council, and the profile of these 5 members is that one of them is male aged 30, the second one is also male aged 32, the third one is a female aged 45, the fourth one is a female aged 20, and the last one is male of aged 40. Now, this Management Productivity Council wants to elect one of the 5 members as their spokesperson. Now, the question is, what is the probability that the spokesperson will be either female or over the age of 35? So, again we are interested here to find the probability of A union B, where the event A denotes that the selected person is a female and event B denotes that the selected person's age is over 35. So, applying the rule 1, the probability of f or over 35 is equals to probability of f plus probability that the person is of over age 35 minus probability of f and over 35. The third component is the A intersection B. Since there are 2 females out of 5, so probability of f is 2 by 5, and out of 5 there are only 2 people whose age is about 35. So, this probability over 35 is 2 upon 5, and the probability that the selected person is to be female and over 35, then we have only one possibility, as we can see that there is only one female whose age is above 45. So, the rule 1 gives this probability that the selected person to be designated as a spokesperson is 3 by 5. Let us look at the next rule, and this rule is about the addition rule when events are mutually exclusive. That is, it is a special case of the rule 1. So, if the events A and B are such that their intersection is a null set, then events A and B are said to be mutually exclusive. And then we know that in this case probability of A intersection will be 0. So, from rule 1 we simply get probability of A or B or probability of A union B is simply equals to probability of A plus probability of B. Now, the next rule is about the probability of complement of an event. Now, we have rule 1 as probability of A or B is equal to probability of A plus probability of B minus probability of A intersection B. Now, in this rule if we take B is equals to A bar, then A and B are mutually exclusive and exhaustive events, because by definition A intersection A bar will always be a null set. Therefore, this gives me on the left hand side of rule 1 as probability of A or A bar, that is probability of A union A complement, and this is again by definition this probability is 1. Then on the right hand side this remains as it is, but the second part is probability of A bar, and the third component of the rule 1 is 0, and this gives me the probability of A bar is equals to 1 minus probability of A. Let us see the application of this rule in this example. This is an example about the family size. Here in the first row it is given number of children and it is denoted by x, that is the number of children in a family can be 0, 1, 2, 3, 4, 5 or it may be 6 or more. Then the second row of this table gives the proportion of families having this many children. For example, 0.1 is the proportion of the families who have only one child, and so on. Here suppose I want to find out the probability that x is less than equals to 5, that is the probability that a family consists less than or equal to 5 children. This by definition we can have as equals to probability x is equal to 0 plus probability of x is equal to 1 and so on plus probability of x is equals to 5, and putting the values of these proportions we get this probability as 0.95. Now, the same probability of x less than equals to 5 we can obtain alternatively by using the rule 3. Here if I take this x less than equals to 5 as my set A or event A, then this x greater than 5 will be the complement of set A. So, by applying the rule that probability of A is equals to 1 minus probability of A complement, this gives me the probability that x less than is equals to 1 minus probability that x is greater than 5, which is equals to 1 minus probability that x takes value 6, and this gives me the same probability. We have discussed rule 1 for 2 events, which can be extended for more than 2 events also. For example, for 3 events, this rule will be that probability of A or B or C is equals to probability of A plus probability of B plus probability of C minus probability of A B minus probability of A C minus probability of B C plus probability of A intersection B intersection C. And if A, B and C are mutually exclusive events, that is the A intersection B is a null set, A intersection C is also a null set and B intersection C is also a null set, then this rule simply converges to that probability of A or B or C is equals to probability of A plus probability of B plus probability of C. Now, we shall discuss about the statistical independence of events or simply the independence of events. Here the independence of events has a different meaning than what we have in the literary sense. In terms of the probability, two events A and B are said to be independent if and only if probability of A intersection B can be written as the product of the two probabilities, that is probability of A and probability of B. This is also known as product probability property of probability theory. Now, let us talk about the pairwise and mutual independence of events. When we have more than two events, for example, when we have three events A, B and C, then they are said to be mutually independent if the conditions given in 1 and 2 are satisfied. In the one, that is probability of A B is equals to probability of A multiplied by probability of B, probability of B intersection C is equals to probability of B multiplied by probability of C, and probability of A intersection C is equal to probability of A times probability of C. That is, the events A, B and C are pairwise independent, and the last condition is that probability of A intersection B intersection C is equals to probability of A times probability of B times probability of C. So, the conditions given in first bracket, it defines the pairwise independence of the events, and the conditions given in 1 and 2 defines the mutual independence of events A, B and C. Now, let us look at this example of tossing of two fair dice. We know that in tossing of two fair dice experiment, there are 36 possible outcomes. For example, this outcome 2, 3 means that the 2 comes on the first die and 3 occurs on the second die. So, this way we have the outcomes as 1 1 2 1 6, 2 1 2 2 6 and so on 6 1 2 6 6. So, there are 36 possible outcomes in this experiment, or we can say that our sample space contains 36 elementary events. So, here the value of n is 36. Now, here I define event A as the first die shows 5 or 6, that is, on the first die a digit 5 or 6 can come, but on the second die we do not have any restriction. In that case, we have the elementary events given in the last two rows, that is 5 1 2 5 6 and 6 1 6 2 2 6 6 are the favorable cases of this event A, and therefore, by classical definition of probability, this is equals to 12 by 36 or it is equal to 1 by 3. Now, the events B defines as the second die shows 5, that is, on the second die the digit 5 occur, whereas on the first die we do not have any restriction. In that case, the outcomes or the elementary events given in the fifth column, that is 1 5, 2 5, 3 5, 4 5, 5 5 and 6 5 are the favorable cases to event B, that is my M here is 6, and this gives me the probability of B as 6 upon 36, which is equals to 1 upon 6. Now, I define the event C as both dies show the same face value, that is the same number. That is, if digit 1 occurs on first die, then digit 1 occur on the second die also. So, that way 1 1, 2 2, 3 3, 4 4, 5 5, 6 6, that is all the elementary events given in this diagonal of this say matrix. So, this probability of C is 6 upon 36 by using the m by n definition of the probability. Now, if we take the intersections of A and B and A and C and of B and C, then the A intersection B gives me the elements 5 5 and 6 5, and A intersection C gives the 5 5 and 6 6, and B intersection C will contain only elementary event 5 5. And if I take the intersection of A, B and C, that is, I am taking the common elements of set A, B and C, then again it is only 5 5, that is only one elementary event is common to all the 3 events A, B and C. So, again if I calculate the definition of probability of A intersection B, then it is 2 upon 36, and I observe that this is equals to probability of A times probability of B, and probability of A intersection C again is 2 by 36, as A intersection C consists only 2 favorable cases, and this again I observe that it is equals to probability of A times probability of C. And similarly, as B intersection C consists only one elementary event, therefore, probability of B intersection C is equals to 1 upon 36, and you will observe that this can be written as the product of probability B and of probability of C. So, looking at this result, we can say that my events A, B and C are pairwise independent, but the question is, are they mutually independent also? So, the events A, B, C are pairwise independent, but however, we observe that probability of A intersection B intersection C is not equals to probability of A times probability of B times probability of C. This implies that the events A, B, C are not mutually independent, but they are only pairwise independent. So, in general, the result given in 2 does not imply the results given in 1, and at the same time the results given in equation 1 does not imply the result given in equation 2. So, we can conclude that pairwise independence need not imply mutual independence of events. Let us look at one more result on independence of events, that is, for two events A and B in the sample space S, if A and B are independent events, then A and B complement will also be independent, and complement of A and B events will also be independent, and also the A complement and B complement will be independent events. Here we know that AC and BC denotes the complements of set A and of B in the sample space S. That is, mathematically we can write this result as, if probability of A intersection B is equals to probability of A times probability of B, then probability of A intersection B complement is equals to the product P of A and P of B C, and P of A C intersection B is equals to the P of A C times P of B, and P of AC intersection BC will be equal to probability of AC times probability of BC. So, today in this lecture, we have first discussed the relative frequency approach to probability and then discussed some important rules like the addition and multiplicative laws, and then finally, we discuss about the statistical independence or the independence in terms of probability of events, and in particular we talk about the pairwise and mutual independence of events. We shall continue our discussion of the probability theory in forthcoming lectures also. Thank you.